Everyone, in this video we are going to discuss about nickel exploration. Of course, nickel is quite common compared to other metallic elements, but its usages are increasing day by day. There are so many usages. Everything we will be discussing in this video. So let's begin. So in the beginning, this background photo itself is a uh, typical photo of outcrop pattern where nickel can be found. It is mostly associated with sulfides in Gaussian. Most importantly, if we see the overall color, it is quite dark. Okay, so these are mostly found in association with mafic, ultramafic rock complexes. There are so many geological significance. So before proceed into detail, let us have some introductory idea, because nickel mostly found in two types of occurrence. Mode of occurrence wise, if we see, it is of two types: magmatic and lateritic. Most important thing is magmatic. Lateritic is different phenomena I will discuss. This magmatic, there is directly from magma this metal gets deposited, because nickel is incompatible element, compatible element. It can enter easily into earliest crystalline phases. Whatever crystal forms earlier, as per bounce reaction series, if you can see olivine and these kinds of FeMG rich minerals, in that nickel also readily accommodated. Okay, so therefore initial phase of magmatic crystallization, whatever rock formed during that particular initial phases, nickel gets deposited in that preferential. And apart from that, lateritic nickel deposits are also results from intense weathering of same ultramafic rock only, but there are difference, because magmatic nickel deposits, sulfide related deposits, are mostly found with particular typical ore, nickel ore. Okay, those things will be discussed. For lateritic nickel phenomena, that ore is different. So overall fundamental mineralization process involves segregation. Fundamental means we will be discussing on magmatic first. Lateritic is replica, later process. Okay. So let us first discuss with magmatic sulfide, in which fundamental mineralization process is mainly related to segregation of immiscible sulfide magma from a silicate magma. Ultramafic complex comprises of different FeMG, nickel, cobalt, so many, everything, so many elements within that fluid. Within that, sulfur is also one of that element. When silica rich fluid and sulfide rich fluid coexists, it cannot mix together like oil and water. So automatically sulfur rich fluids gradually separated. It is called phase separation. So with progressive accumulation, they segregate separately. So in that way, they gradually move away from silicate magma, and silica rich magma further proceed upwards. And since this sulfide rich magma in reducing condition preferentially attract heavy element like nickel, copper, platinum group of elements like platinum, palladium, so they preferentially are heavy and settle down below, and silicate rich magma try to go upward. So nickel, copper, platinum group of elements have very strong tendency to partition into sulfide liquids, as I have mentioned. Now geological setting, this is quite interesting. First, see magmatic layered complex. What are they? Because magma can also show stratification. Yes, of course, there may be layering is possible, because generally layered intrusive complex include as very large lens-shaped bodies, as it is showing here. I am showing here. They crystallize deep in the crust, and as we know, fundamental primary magma are mostly mafic and ultramafic types. So it is very less differentiated. Pyroxenite, dunite, gabbro, this dark green, black, these kinds of mineral rich magma found in association with another felsic rock, that is anorthosite. Very interesting thing, because anorthosite is exceptional rock because that is basic ultra basic rock, but not mafic or ultramafic. The composition, if try to understand, mafic terminology is used based on color index, FEMG minerals, whereas chemical terminology, so mafic and felsic are field based terminology, whereas geochemical terminology is basic and acidic. Because until and unless you are analyzing the rock and get the SiO2 content, you cannot say whether that is acidic or basic. But by visually estimating the color, directly you can say based on color index whether it is mafic or felsic. Usually all mafics are usually found as basic, ultramafic or ultra basic, but anorthosite is exception. Anorthosite's SiO2 content is very less. According to proper geochemical data, you can see 45 to 52% SiO2 content called basic, and less than 45% SiO2 is called ultra basic. So in case of anorthosite, SiO2 usually basic to ultra basic range, but color wise it is of course felsic. Okay, so overall anorthosite can also hold sometimes copper and this kind of nickel deposits in association with mafic, ultramafic, other basalt, gabbro, sorry basalt, no not basalt, gabbro, this plutonic complex, okay, dunite, pyroxenates, etc. Pyrrhotite. So source of the most of the world's nickel are PGE, chromium minor source. Copper is very less because copper, lead, zinc, there are different types of deposits, okay. But sometimes in PGE also, in these types of magmatic also deposit also copper found, but most generally, most likely it is found in hydrothermal setting, okay, and of course Gaussian like setting. In Gaussian, these kinds of things are found that I will be discussing, that is separately I will be discussing, that is coming under lateritic type. Then I'll bring that context, okay. So overall, primary magma, see, try to understand the host rock formation itself, the process of enrichment, that process of mineralization, that element, that metal concentration itself is directly related to rock, host rock formation. That, so therefore entire host rock package comprises of cumulate, accumulation of these kinds of metal. So this complex vary in size, but generally bigger is better, generally more than 1 million kilometer cube, huge volume, okay. Area wise also it spread a lot. Overall, copper nickel associations are relatively lesser in dimension as compared to PG chromium deposits, as it is observed in general. So overall, see, for copper and nickel, we will be focusing in this context mainly on nickel. So main thing is that magma, of course, most of the magma comprises of nickel. Any ultramafic magma comprises of nickel. But how that nickel can get deposited? For that, sulfur, presence of sulfur is must. That sulfur is very much important thing, and most of the sulfurs cannot be found within the magma system itself from the beginning. It usually scavenges from surrounding rocks, okay. Sulfur mostly when magma comes up from surrounding rock, magma absorbs sulfur, like pyrite. Whenever country rock comprises of pyrite, those pyrite will be accumulated, they will be assimilated with that magma, and in turn the magma sulfur content will be increasing, and therefore that sulfur, when melt, that sulfur within that magma system will be separated. Those sulfur rich magma cannot mix with that silicate rich magma, and eventually that sulfur will be going along with these chalcopyrite metals. Okay, so chalcopyrite, pyrite, sometimes then other pentlandite, these kinds of mineral forms. So sulfide melt separates from magma like drop of water in oil. Okay, and it go below, since that heavy copper, nickel and platinum group, chromium, palladium, these kinds of elements will be associated, it will be automatically preferentially go down. So overall, sulfide saturation process is very much important, and initial presence of nickel is in general always high because it is fifth most common element. So most important thing is to have sulfide liquid. Okay, this may separate from the magma. So overall, addition of sulfur is not only the process of sulfide saturation in reducing condition, rather decreasing FeO content, increasing partial pressure fugacity of oxygen, reducing temperature, increasing pressure, these are also sometimes important factor. Okay, overall complex assimilation, that means mixing with host rock, as I have mentioned, fractionation, because silica rich magma will go down and other initial phase minerals sometimes separated, and contamination process in high energy magma chambers are likely to provide opportunities for sulfide saturation. So overall, primary magmatic sulfides have a distinctive sulfide assemblages. Variation from these inevitably reflect post-ore processes. I will be showing the layered complex. In general, you can see though sulfide rich these kinds of deposits, primary deposits of nickel are mostly associated with mafic to ultramafic and basic to ultrabasic. Okay, so these are the mineral stability field: olivine, pyroxene and calcium rich plagioclase, that is anathrosites. These kinds of rock can hold. As we can see, this is very commonly known. In this direction, of course, silica content increase, this is decreasing, and in this direction you see iron, magnesium, calcium, nickel, they will be increasing. Similarly, sodium, potassium will be decreasing. Okay, and overall their temperature is 1200 degrees Celsius. So layers of alternating mafic and ultramafic rocks are important phenomena in layered complexes, and mafic layered complexes are generally very large, shaped, pancake-like, as I have shown earlier. Of course, they will be having some feeder channel from which that magma will come up. Due to high initial heat and deep burial, they tend to cool slowly, and therefore overall coarse grained mafic and ultramafic rocks like pyroxenides, dunites, gabbros, ultra-anathrosites, they can hold this. But overall, few salient point you must remember, because you should not expect that the rocks are always black or dark green, as I have mentioned initially, because anathrosite, that is calcium plagioclase rich ultra basic or basic rocks, can also have white color. Okay, they are not mafic, but of course basic. High Ni contents, high nickel content in mafic ultramafic magma is not uncommon. Okay, but sulfur content is more important. When magma intrudes the host rock, it assimilates those host rock and any sulfur that they may contain, those host rock may contain, in the form of pyrite or chalcopyrite or whatever. If this host rock don't contain enough sulfur, these ore deposits cannot form usually. That is difficult. In that case, these become difficult. So therefore, wherever we are getting sulfide related primary magmatic nickel deposits, of course, host rocks, surrounding host rocks must have to be supplied sulfur. So sulfur containing host rock is essential. Okay, and of course when that sulfur rich fluids form, it will be automatically separated like oil and water. So overall Boyle's reaction series, if we see, of course from this part of this part, both the parts, see initial phase around 1200 to 1000 degrees Celsius, magnesium and iron rich olivine, pyroxene, calcium rich plagioclase. So this domain, this is the area where these kinds of magmatic nickel sulfides can form. Okay, so initially Mg, Ca, Fe and nickel, this will be accompanied. Overall, including mafic magma rich in copper and nickel is must, and of course magma has to absorb sulfur from surrounding area, as I have mentioned. Okay, these things already I have mentioned. So overall, now basic principle, if we see, it is why it is not coming. There is beautiful photographs. Let me check once more. It will come. So in general, if we see the nickel property, it is silvery white. Nickel is of course silvery white. Its density is 8.9. Its melting point is around 1450 degrees Celsius. Boiling point is around 2900 degrees Celsius. Its Mohs scale of hardness, according to that, its hardness is 4. Okay, apatite like. Okay, tells you some chloride apatite. Okay, apatite like. Atomic number is 28, and chemically it is not that much reactive, corrosion resistant. Magnetic property it is there, just like iron, ferromagnetic. Okay, electric conductivity, it is a good conductor. Alloying properties are there. And overall, if we see the mineralogy of nickel ore, commonly nickel minerals include pentlandite, millerite, okay, nickel silicate, nickel sulfide. Pentlandite is iron nickel sulfide. Then pyrrhotite, pyrrhotite in formula of course Fe1 minus XS, but of course nickel is present. Okay, that is not shown in mineral formula because it is little bit lesser, but always present most of the times. Chalcopyrite also can hold nickel. Then garnierite, nickel rich ferrosilicate, nickel bearing serpentine, and sometimes in physically adsorbed from nickel cobalt can be associated with goethite, hematite, limonite as well, and sometimes nickeliferous serpentine. All can hold nickel. Overall mineralogy, if we understand, now let us go back to the actual photographs. If I am making it full, it is not coming. Okay, so overall if we see these kinds of Gaussian, so entire area is highly weathered, see, chemically weathered, and oxidized, but this is lower portion of Gaussian is mostly preserved. So lot of sulfides you can see, yellowish color, and this area, this water also yellow in color, and you can see where I am moving that cursor, lots of color you can see, pyrite, bleeding, oxidation, environment condition, where main criteria you can see the typical Gaussian like features, intensely weathered profile with sulfur like smell. Once you will visit those kinds of places, you can smell just like barud. Barud means crackers. When you utilize cracker, that time whatever smell you can get, same smell you can feel. High nickel content, high sulfur content, higher nickel by cobalt ratio, distinct trace element signatures like copper, cobalt, platinum group elements, chromium, these things will be more. Whenever you collect sample, get analyzed, these things will be more. And overall ultramafic rock complex, which will be intensely deformed, weathered. So in close view, we see these are some field photographs. Okay, you see these are how much pyrites, how much sulfides present, intense sulfide presence. Okay, along with that, these black minerals, there are nickels. Sometimes nickels present. If we analyze, that time will be better understand. And this is way that intensely limonitized, but these are the ore, major ore. How does it look like? You can see. Now, overall production and use, if we see, maximum production is coming from mostly Russia, then Canada, Indonesia, Australia. Okay, this chart, from this chart you can pause, you can see, and overall use you can see mostly in alloy industry and stainless steel. Of course, stainless steel highest, then alloy, different type of alloy, and electroplating also. So about 30% of the global nickel production comes from magmatic sulfide type deposits, and remaining 64% come from nickel rich laterites. Nickel rich laterites from Gossan. Okay, in case of Gossan, there are different mineralogy, as I have shown. These are Gossan like features. Okay, and even fresh sulfide deposits, fresh magmatic also sometimes from Gossan like features in the top portion. But in case of typical laterite Gossan, lateritic profile, whatever thing found in case of laterite, same features you can get. Okay, several profiles. And then once you identify Gossan, then rusty, weathered cap, limonite, hematite rich boxwood texture you can have to identify, and mineralogy also you need to check, because these Gossan should be on ultramafic complex. Whatever laterite or bauxite deposit you can get, those are found on felsic rocks. Okay, this is mafic we are talking about. And secondary alteration minerals are very much essential to understand, like serpentine, talc, different carbonates. Okay, late stage hydrothermal impact imprint can also happen sometimes. Okay, so those things also you need to take care. Overall, if you see, these are the typical features. How does it look like? These are not like Gossan. This is a typical characteristics developed due to sulfides. Okay, this is a typical coloration. In case of Gossan, you need to identify oxide zone at the top. Below that, below water table, you need to have that reducing zone. As you must be knowing the generalized concept of Gossan. This is typical magmatic sulfides. Okay, see how does it look like. Now, according to the overall idea, after having the overall idea, now you need to guess what are those minerals. That is not so easy task, but of course these are not words, try to understand. These are kyanite, okay, bluish tint. But what about these? Here you can see black dots. These are euhedral, of course. When you zoom in, you can understand. Most probably these are some secondary minerals or primary. These things I also could not understand, so for that I need to do petrography. So far just it is a recent work made by our fellow junior colleagues. Okay, of course these are kyanite, they have identified. These are taken from Africa. With this, thank you. I hope it is an interesting